There are three major structures in Oracle Database Server architecture: memory structures, process structures, and storage structures. A basic Oracle database system consists of an Oracle database and a database instance. The database consists of both physical structures and logical structures. Because the physical and logical structures are separate, the physical storage of data can be managed without affecting access to logical storage structures. Each database instance is associated with one and only one database. If there are multiple databases on the same server, then there is a separate and distinct database instance for each database. A database instance cannot be shared. A real applications cluster, RAC, database usually has multiple instances on separate servers for the same shared database. In this model, the same database is associated with each RAC instance, which meets the requirement that, at most, only one database is associated with an instance. A connection is a communication pathway between a user process and an Oracle database instance. A communication pathway is established using available inter-process communication mechanisms on a computer that runs both the user process and Oracle database or network software when different computers run the database application and Oracle database and communicate through a network. A session represents the state of a current user login to the database instance. For example, when a user starts SQL+, the user must provide a valid username and password, and then a session is established for that user. A session lasts from the time a user connects until the user disconnects or exits the database application. Two basic memory structures are associated with an instance: System Global Area, SGA, group of shared memory structures, known as SGA. Components that contain data and control information for one Oracle database instance. The SGA is shared by all server and background processes. Examples of data stored in the SGA include cached data blocks and shared SQL areas. Program Global Areas, PGA, memory regions that contain data and control information for a server or background process. A PGA is non-shared memory created by Oracle Database when a server or background process is started. Access to the PGA is exclusive to the server process. Each server process and background process has its own PGA. The shared pool portion of the SGA contains the library cache, the data dictionary cache, the server result cache containing the SQL query result cache and the PL, SQL function result cache, buffers for parallel execution messages, and control structures. The data dictionary is a collection of database tables and views containing reference information about the database, its structures, and its users. Oracle Database accesses the data dictionary frequently during SQL statement parsing. This access is essential to the continuing operation of Oracle Database. The database buffer cache is the portion of the SGA that holds block images read from the data files or constructed dynamically to satisfy the read consistency model. All users who are concurrently connected to the instance share access to the database buffer cache. The first time an Oracle Database user process requires a particular piece of data, it searches for the data in the database buffer cache. If the process finds the data already in the cache, a cache hit, it can read the data directly from memory. If the process cannot find the data in the cache, a cache miss, it must copy the data block from a data file on disk into a buffer in the cache before accessing the data. Accessing data through a cache hit is faster than accessing data through a cache miss. The redo log buffer is a circular buffer in the SGA that holds information about changes made to the database. This information is stored in redo entries. Redo entries contain the information necessary to reconstruct, or redo, changes that are made to the database by DML, DDL, or internal operations. Redo entries are used for database recovery if necessary. The database administrator can configure an optional memory area called the large pool to provide large memory allocations for session memory for the shared server and the Oracle XA interface, used where transactions interact with multiple databases, I/O server processes. Oracle Database Backup and Restore Operations. Parallel query operations. Advanced queuing memory table storage. By allocating session memory from the large pool for shared server, Oracle XA, or parallel query buffers, Oracle Database can use the shared pool primarily for caching shared SQL and avoid the performance overhead that is caused by shrinking the shared SQL cache. Java pool memory is used to store all session-specific Java code and data in the Java Virtual Machine, JVM. Java pool memory is used in different ways, depending on the mode in which Oracle Database is running. The Streams pool is used exclusively by Oracle Streams. The Streams pool stores buffered queue messages, and it provides memory for Oracle Streams capture processes and apply processes. Unless you specifically configure it, the size of the Streams pool starts at 0. The pool size grows dynamically as needed when Oracle Streams is used. The Program Global Area, PGA, is a private memory region containing data and control information for a server process. Each server process has a distinct PGA. Access to it is exclusive to that server process and it is read only by Oracle code acting on behalf of it. It is not available for developers' code. Every PGA contains stack space. In a dedicated server environment, each user connecting to the database instance has a separate server process. For this type of connection, the PGA contains a subdivision of memory known as the User Global Area, UGA. The processes in an Oracle database system can be divided into three major groups: user processes that run the application or Oracle tool code, Oracle database processes that run the Oracle database server code, including server processes and background processes, Oracle daemons and application processes not specific to a single database. Oracle Database creates server processes to handle the requests of user processes connected to the instance. The user process represents the application or tool that connects to the Oracle database. It may be on the same machine as the Oracle database, or it may exist on a remote client and use a network to reach the Oracle database. The user process first communicates with a listener process that creates a server process in a dedicated environment. Background processes. To maximize performance and accommodate many users, a multi-process Oracle database system uses some additional Oracle database processes called background processes. An Oracle database instance can have many background processes. The database writer process, DBWN, writes the contents of buffers to data files. The DBWN processes are responsible for writing modified, dirty, buffers in the database buffer cache to disk. Although one database writer process, DBW0, is adequate for most systems, you can configure additional processes to improve write performance if your system modifies data heavily. The additional processes are named DBW1 through DBW9, DBWA through DBWZ, and BW36BW99. These additional DBWN processes are not useful on uniprocessor systems. The log writer process, LGWR, is responsible for redo log buffer management by writing the redo log buffer entries to a redo log file on disk. LGWR writes all redo entries that have been copied into the buffer since the last time it wrote. LGWR starts and coordinates multiple helper processes that concurrently perform some of the work. LGWR handles the operations that are very fast, or must be coordinated, and delegates operations to the LGNN that could benefit from concurrent operations, primarily writing the redo from the log buffer to the redo log file and posting the completed write to the foreground process that is waiting. A checkpoint is a data structure that defines a system change number, SCN, in the redo thread of a database. Checkpoints are recorded in the control file and in each data file header. They are a crucial element of recovery. The System Monitor Process, SMON, performs recovery at instance startup if necessary. SMON is also responsible for cleaning up temporary segments that are no longer in use. If any terminated transactions were skipped during instance recovery because of file read or offline errors, SMON recovers them when the table space or file is brought back online. SMON checks regularly to see whether the process is needed. Other processes can call SMON if they detect a need for it. The Process Monitor Process, PMON, performs process recovery when a user process fails. PMON is responsible for cleaning up the database buffer cache and freeing resources that the user process was using. For example, it resets the status of the active transaction table, releases locks, and removes the process ID from the list of active processes. PMON periodically checks the status of dispatcher and server processes, and restarts any that have stopped running, but not any that Oracle Database has terminated intentionally. The Recoverer process, RECO, is a background process that is used with the distributed database configuration that automatically resolves failures involving distributed transactions. The RECO process of an instance automatically connects to other databases involved in an in-doubt distributed transaction. When the reco process re-establishes a connection between involved database servers, it automatically resolves all in-doubt transactions, removing from each database's pending transaction table any rows that correspond to the resolved in-doubt transactions. And dispatcher processes with the Oracle Net Listener. LREG provides the listener with the following information: names of the database services, name of the database instance associated with the services and its current and maximum load, service handlers, dispatchers and dedicated servers, available for the instance, including their type, protocol addresses, and current and maximum load. The archiver processes, ARCN, copy redo log files to a designated storage device after a log switch has occurred. ARCN processes are present only when the database is in ARCHIVELOG mode and automatic archiving is enabled. If you anticipate a heavy workload for archiving, such as during bulk loading of data, you can increase the maximum number of archiver processes. There can also be multiple archive log destinations. It is recommended that there be at least one archiver process for each destination. The default is to have 4 archiver processes. The files that comprise an Oracle database are as follows. Control files. Each database has one unique control file that contains data about the database itself, that is, physical database structure information. Multiple copies may be maintained to protect against total loss. It can also contain metadata related to backups. The control file is critical to the database. Without the control file, the database cannot be opened. Data files contain the user or application data of the database, as well as metadata and the data dictionary. Online redo log files allow for instance recovery of the database. If the database server crashes and does not lose any data files, the instance can recover the database with the information in these files. The database has logical structures and physical structures. Databases, tablespaces, and data files. The relationship among databases, tablespaces, and data files is illustrated in the slide. Each database is logically divided into 2 or more tablespaces. 1 or more data files are explicitly created for each tablespace to physically store the data of all segments in a tablespace. If it is a temporary tablespace, it has a temporary file instead of a data file. A tablespace's data file can be physically stored on any supported storage technology. A subset of database objects such as tables and indexes are stored as segments in tablespaces. Each segment contains 1 or more extents. An extent consists of contiguous data blocks, which means that each extent can exist only in one data file. Data blocks are the smallest unit of I/O in the database. A database is divided into table spaces, which are logical storage units that can be used to group related logical structures. 1 or more data files are explicitly created for each tablespace to physically store the data of all logical structures in a tablespace. Each Oracle database must contain a system tablespace and a SYSAUX tablespace. They are automatically created when the database is created. The system default is to create a small file tablespace. You can also create big file tablespaces, which enable the Oracle database to manage ultra-large files. A tablespace can be online, accessible, or offline, not accessible. The system tablespace is always online when the database is open. It stores tables that support the core functionality of the database, such as the data dictionary tables. A pluggable database, PDB, is a set of database schemas that appears logically to users and applications as a separate database. But at the physical level, the multi-tenant container database, CDB, has a database instance and database files, just as a non-container database does. The graphic in the slide shows a CDB with 4 containers, the root, the seed, and 2 PDBs. The 2 applications, HR and sales, use a single instance and are maintained separately. At the physical level, the CDB has a database instance and database files, just as a non-CDB does. Automatic Storage Management, ASM, provides vertical integration of the file system and the volume manager for Oracle database files. ASM can provide management for single symmetric multiprocessing, SMP, machines or across multiple nodes of a cluster for Oracle. Real Application Clusters, RAC, support. ASM does not eliminate any existing database functionality. Existing databases are able to operate as they always have. New files may be created as ASM files, whereas existing ones are administered in the old way or can be migrated to ASM. The diagram illustrates the relationships between an Oracle database data file and the ASM storage components. The crow's foot notation represents a one-to-many relationship. An Oracle database data file has a one-to-one relationship with either a file stored on the operating system in a file system or an ASM file. The following example describes Oracle database operations at the most basic level. It illustrates an Oracle database configuration in which the user and associated server process are on separate computers, connected through a network.